One of the main challenges of autonomous driving is capturing reliable measurements of the environment. In this video, we discuss some of our approaches to sensing with applications in self-driving. The performance of the state-of-the-art sensing technologies is one of the major impediments towards the realization of autonomous driving. Given the limitations of current sensors, a multitude of sensing modalities, including radar, sonar, vision, and LiDAR, are currently used. This increases costs and relies on computationally expensive and often inefficient sensor fusion algorithms. Even then, slight changes in weather conditions can generate significant challenges. In our research, we aim to design low-cost and efficient sensing hardware and software, as discussed in the next few slides. Vision carries a lot of information about the environment. In one of our approaches to sensing, we augment the vision data with depth information using active optics. On the left, you can see a grayscale camera image, and on the right is corresponding depth map obtained based on our methodology. In our approach, we use a membrane active lens for imaging, one that can deform and change its focal length. By mechanically actuating the lens, we can move the focal plane of the camera back and forth at high speed. For every sweep of the focal plane, various objects come into focus at different times depending on their distance to the camera. By quantifying focus at different pixels, it's possible to locate objects as is schematically shown in the figures at the bottom of the slide. For objects that are closer to the camera, the corresponding focus measure will feature two peaks that are far apart. As the object moves farther away from the camera, the peaks come closer to each other. By modeling the focus variations, we can find a relatively accurate estimate of the location of various objects in the view of the camera. This slide shows an example video on how the method works. The video on the right shows the variations of the focus measure at different pixel points. Initially, the focal plane resides very close to the camera and gradually moves away towards the farther object. As each of the two objects come into focus during the sweep, their corresponding pixels light up. Here you can see an example depth map obtained based on this approach. The method is low cost, relatively accurate, and reliable, especially for closer distances. For farther objects, the increase in focal depth, however, limits the capabilities of the method. Another very powerful sensing method is light detection and ranging. LiDAR technology is probably the most potential for the future of self-driving vehicles. However, the state-of-the-art LiDAR technology cannot meet the needs of autonomous driving. Current designs perform at relatively short ranges, are very limited in rain, capture low-density point clouds, have low resolution, and most importantly, are bulky and expensive. Many of these limitations can be avoided by redesigning various aspects of the instrument. We have designed a new LiDAR system that uses an array of scanning mirrors. Each mirror component is relatively small with less than a square centimeter area and is mounted on a resonating base. These mirrors can all oscillate synchronously at resonance to scan a laser beam on the surrounding and capture the returning light at the same time. Here you can see a schematic design of our approach. It includes a light source, which is often a laser diode. The generated light is collimated and guided towards one of the mirror components of a scanning mirrors array and is subsequently projected on the surrounding. On the reflection, the scanning mirrors array forms a very large effective aperture to capture a large portion of the reflected light. Furthermore, due to the directional focus of the LiDAR, only the reflections that match the direction of the laser projection are captured. This enables the LiDAR to work at very far distances and in adverse weather conditions. The reflected light is guided by the same oscillating mirrors to a lens and focused on a single detector. The method also includes frequency modulation techniques that improve signal quality and increases point cloud density. Another important benefit of our LiDAR is its compact design. The system can easily fit in the headlight or taillight space in the car. One of the directions that we plan to explore further is on operating the LiDAR in the visible spectrum, so that it can work both for ranging and illumination. In this form, in the future, in addition to illuminating our surroundings, another function of headlights and taillights is to detect obstacles. Given our full control over the direction of light projection, our design opens up other new possibilities in active illumination, for example, to avoid blinding upcoming drivers at night, or to steer lighting to the road curvature in turns. There are many other possibilities in this area for communication, distributed sensing, or even entertainment.